Hey guys, welcome to your Chapter 4, Lesson 3 notes on patterns and nonlinear functions. By the end of the day, you'll be able to identify and to represent patterns that describe nonlinear functions. Now, when we talk about functions, remember that a function is a relationship, it's a rule, it's a pattern, and it pairs each input value with exactly one output value. We looked at our inputs as our independent variables, and our outputs are values of our dependent variable. So in here we have the relationship between the number of steps in a staircase and the number of blocks needed to create that staircase. What this means is if we have one step, we make one block. Okay? We need one block. However, to make our second step, we have 2 blocks. And then in our third step, we add 3 more, making 3 blocks. So this time we added 2, and then we added 3, and then we'll add 4 to give us 10. So we add 1, 2, 3, 4. Well, next time we need to add 1, 2, 3, 4, 5. So when we add 5 blocks, that gives us 15. We can also write these as an ordered pair by taking the number of steps, which is our independent variable, our inputs, and writing them as our first coordinate in a pair, assuming that's a straight line. There we go. And then by taking the number of blocks, which is our dependent variable, because the number of blocks depends on the number of steps we have. We can put those in to our second coordinate in our ordered pair. So we have 1, 1, 2, 3, 3, 6, 4, 10, and 5, 15. Follow that pattern and see if you can figure out how many steps it would take, or how many blocks you need for 6 steps. So let's look at the number of steps column. Does the column for number of steps reflect a constant increase or a constant decrease in values? If so, what's that change? Well, here we look at the number of steps, and each time it increases by 1. So our steps increase by 1 every time. So that's a constant increase plus 1 every time. What about for number of steps? Is that a constant increase or decrease in values? Well, it certainly is an increase to like plus, 1, 3, 6, 10, and 15. That's increasing, but it's not increasing at the same rate. We're taking a step of 2, and then of 3, and then of 4, and then of 5. So it is not a constant increase. You're like, no, it's not constant. It's an increase, but it's not constant. So is this relationship a function? Well, yes, because there is a pattern, and it's not like you have a different number of blocks for the same number of steps. It's not like it takes 2 blocks to make 1 step, but also 1 block to make 1 step. This is a function, but it's not a linear function because the change is not constant. Now we have a very special word. Prepare to have your mind blown. We have a very special word for functions whose graph is not a line or not a part of a line. Remember that a linear function means the graph is a line. Okay, that's linear. And now if you have a graph that is not a line, that's called non-linear. Not great. Non meaning not, and linear meaning line. So there you go. Non-linear means not a line. Ta-da! Now, any functions, in fact, linear or nonlinear, can be represented with 5 ways. 1, you can represent them with words by just talking or writing about what you see. You can represent them with tables. Tables look like an x value and then the y value that goes with it. You can also represent them with equations. Examples of equations that are nonlinear are y equals x squared. That's a quadratic. Or you can have like y equals the square root of x. That's a square root function. And others. So what we have words, tables, equations. You can also represent functions as a list or a set of ordered pairs. Now we call them ordered pairs because the order matters. They're always going to be an x value followed by a y value. You keep them the same so we know what you're talking about. Ordered pair because order matters. And then finally, you can represent a function, which is my personal favorite way, as a graph. A graph is just a picture of what it looks like. So a nonlinear function is anything that's not linear. That's not linear. It's super curvy. Or sometimes you'll have a function that looks like this. Great, right? There you go. 5 ways to represent nonlinear functions. Let's ask the most basic question. Is it linear or is it nonlinear? Remember, linear means line. So basically, all you have to do is determine, is it a line? Number 1, yes, this is a line. So we'll say this is linear. Sweetums. Next, on this one, this is not a line, so this is non-linear. This one is not a line, so this is non-linear. And this one is a line. You can hardly even see it because it's just a horizontal line. So because it's a line, it is linear. Yay! Okay, great, but now let's map it out. I'm going to give you 3 examples, and we'll call it a day. So with our first one, we're going to deal with some pizza. So the area, oh look, we have area right here. The area in square inches of a pizza is a function of its radius r in inches. The cost for the sauce of pizza is a function of the weight of the sauce used. Graph the functions shown by the table below. Is each function linear or is it non-linear? Okay. Well, is each relationship shown in the table a function? Well, it literally says is a function and is a function. So yes, because the instructions tell us, yes, they are both functions. You can also tell because there's only one output for each input. It's not like a 2-inch pizza has 12 square inches, but also 50 square inches. That's not how that works. Each maps to 1, so that counts. Same thing here. It's not like 2 ounces cost 80 cents, also 2 ounces cost 5 cents. No, they only map with 1, so they are functions. Now, how do I classify the functions? Are they linear or are they non-linear? I don't know. Let's look at a graph. So let's use graphs to represent each table. Okay, let's put area on this guy. You know what? We'll make him like the color of pizza. Color's pizza. There you go. So this is pizza area. And we'll put the pizza cost, or sorry, the sauce on the other one. Nice. Okay. So what we're going to do is we are going to put our dependent variable on our vertical axis. So area will go here, and we'll put our independent variable, which is the radius of the pizza, here. Same pattern on this graph. You're always going to put the independent variable, which is weight, horizontal, and the dependent variable, which is cost, vertical. Okay, here we go, area. So I see that, oh wait, we need to label our axes, guys. We didn't label our axes. So the radius of the pizza is our independent, that's in inches. And then the area of the pizza is dependent, that's in inches squared, or square inches, if you will. All right, so when a pizza is 2 inches radius, its area is 12. So we go over 2, up 12. Ooh, boy. Okay, well, if that's like 50, 40, 30, 20, 10, sure. I'll be like here. Right, 2 and 12, excellent, okay. Now 4 and approximately 50. So we go over 4, up 50. Okay. And the next we have over 6 up 113. Well, I'm gonna borrow this same kind of metric to help me split it up, putting the 50 right halfway through. So 115 is like right here-ish. So it'll be like right there. Cool. Oops. And then finally, where's my eraser? Oh, not even finally. We go over 8 up to 100. And then over 10 up 314, which is going to be about there. And now we can connect our graph, or connect our points to make our graph. So as we connect these, we notice also, it'd be 0. Oops. 0, 0 down here. But we shouldn't put that on there because it's not on our table. But as you connect like the general trend, it doesn't make a line. It makes kind of this curvy guy, like that. So this is not linear. We can't do one straight line that hits all of them. So this is non-linear. I can tell you right now, it's quadratic because it's squared. So, anyway, now let's do the same thing, but for sauce. Okay, what variables are we looking at for sauce? Well, we're looking at weight and how that influences the cost. So weight in ounces and cost in dollars. So here, let's label our axes. They already have the numbers on them. That's convenient. Who designed these notes for you? We have weight in ounces and cost in dollars. So there you go. Okay, so we have 2 ounces costs 80 cents. It's going to be about there. 4 ounces costs $1.60, just a little bit more than halfway between. 6 is $2.40. We're going up here. Oh, $2.40. Whoops. Just a little bit less than halfway. 8 is $3.20. Over 8 up $3.20 is about there. And 10 ounces costs $4. That's nice because that's right on the crossroads. Now, if I did this right, they should all connect on the same straight line. I didn't connect them right. But there you go. Okay, no, that's not good enough. I need to make straight line. I'm obsessed. Haha! Okay, so I needed to make this point a little bigger. Yes, they do all lie on the same line. So that means the sauce cost is linear. We did it. So is each function linear or non-linear? We got it. Area is not linear, but the cost of the sauce is super duper. So we have a linear function. We have a non-linear function. This is a quadratic. It's doing with squares. Let's look at something that's not. It's not quadratic. It's not linear either. So consider the following. Think of a function as a rule that you apply to the input in order to get the output. We're going to try to figure out what is that rule this time. So here in example 3, we've got this tree. And as this tree grows, it has more and more branches. So when we have our first step, it's got 3 branches. And then in our second step, we multiply by 3 to get 9 branches. In our third step, we multiply by 3. We make each one into 3 to make 27 branches. So find a pattern to complete the table. I kind of just told you what that pattern was. Each step, we're multiplying times 3. So we have times 3, and we need to times 3 again, and we need to times 3 again. So 27 times 3 is 81. And 81 times 3 is 243. Aren't you so glad I didn't have you draw out all those trees? That would take forever. Find a pattern. We did. We found the pattern. Nice. Okay, complete the table. Now we need to write the pattern in words. So to get the next step, you multiply the previous number of branches by 3. And that's our rule. However, you guys, there's not just one singular rule. There's not one way to express the rule. You can say, hey, just take the previous guy and times him by 3. There's another way to look at it. Maybe you looked at this pattern and you saw, hey, the number of the figure, whatever that number is, I called it X, just kidding. If you're on figure number X, all you have to do is take 3 and multiply it by itself that many times to get your Y. So here it's just 3. And then next you have, 3 is just 3 one time. But 9 is 3 times 3. And 27 is 3 times 3 times 3. And 81 is 3 times 3 times 3 times 3. Okay. Another way you can say this is, hey, that's the same thing as 3 to the first power. This is 3 squared. This is 3 cubed. This is 3 to the 4th power. And you guessed it, 243 is in fact 3 to the 5th power. So the pattern here is you just take 3 and you raise it to the xth power. And that gives us our equation. Y here is 3 to the x. That was it. Y equals 3 to the xth power. And now all you have to do is graph it. You just look at the table and you plot those points in. So the number of the figure that we have, so we're like the steps in drawing it, is our x-axis. That's our independent variable. And then the number of branches depends on what step we're on. That's our dependent variable that goes up here. I missed the axis. Fortunately, our numbers are there. We need to label our axes with the headers on our table, what we're talking about, what x is. So we just say number of the figure, or we can say like steps in the drawing, number of the figure, and then number of new branches. Number of new branches on the side. And let's graph it. Okay. Well, our first figure had 3 branches. Oof, boy. It's gonna be like down here. Our second figure had 9 branches. It's gonna be like a 1/5 of this. That's too spread out. It's gonna be like there. Man, that is not a big change. Maybe I made this graph too big. Oh well, our third step had 27 branches, which is a little bit more than halfway. Yep. Okay, still tiny, tiny graph. Our fourth step had 81 branches. Oh, there we go. There's some growth. It was gonna be like here-ish. And then our fifth step had 243. Okay, maybe I did not make this graph too small. Yikes, that's a big step. So then our function looks like this. Our function goes like this. Like that. This is called exponential because it grows exponentially. This is also the way that like disease is transmitted and population grows, is exponential. We call it exponential because x is an exponent here. No. But I didn't ask, is this exponential? I just asked, is this linear? I didn't even ask that. Bonus question, is this linear? No, this is non-linear. Okay, here we go. That's great. But what if we just have ordered pairs? Here we were given a table. Actually, we were kind of given a picture. We made a table from that picture. Here we were given tables. Here we're given pictures. Okay? Well, how can we make a graph using a list? Well, make a table first. We'll make an XY table to organize our values. So we put our X's on one side, put your Y's on the other. One of you had a great question. Does the X always need to go on the right side? And that question is yes, because we read right to left. So our inputs need to go on this side, and our outputs come out the other side. So you know who you are. That was a great question. Way to go. Keep them coming. I love great questions. because they're beautiful. Okay, so you have your inputs on one side, you got your outputs on the other side. We're going to put all our x's on one side and pull our y's on the other side because you guys are such wise guys. Okay, here our first point is 1, 1. Our second is 2, 4. Third is 3, 6. Then we have, nope, just kidding, 3, 9, 4, 16, and 5, 25. Okay, that was the first step. Yay, I love tables. For each rule in the table, identify rules that produce the given y value when you substitute the x value. So we want to figure out, how do I get from the inputs to the outputs? Well, here on our first row, I could say y equals x. I could make that my rule because 1 equals 1. But that doesn't work here because 4 is not equal to 2. So 1 equals 1, that works. And 9 is not equal to 3, so that doesn't work. The y equals x doesn't work. I could look at my second one and I could say, you know what, here y is x plus 2. But in this row, 1 is not 1 plus 2. In the second row, 4 is 2 plus 2, and that's good. But in the third row, 9 is not 3 plus 2. So we're taking the y values from our charts and plugging them into the rule to see if that works, and it's not working so far. Whoa, that's neat. Wrong, but neat. Okay, but as I look here, here's my hint for you. Look at the change in y. Since here y increases by 3, and then by 5, and then by 7, and then by 9, you see that there is a pattern. They are increasing, but the increase changes. So I look at this and I say, you know what? When I look at 4 and 9 and 16, I recognize those all as perfect squares. So let's try y equals x squared. Is it true that 1 equals 1 squared? Yes. Let's look at our next line. Is it true that 4 equals 2 squared? Yes, that's true. Is it true that 9 equals 3 squared? Yes, that's true. So as we plug in our y values and our x values, actually our x values and our y values, in this same rule, we make sure they always work. Yes, they do. Excellent, excellent. Okay. So let's use words to describe the relationship. I'll say, well, each time x increases, y increases more, or y is x times itself. There you go. That's a good way to say that with words. But to say that in algebra, we say y equals x squared. Ta-da! There you go. Okay, so nonlinear functions are functions that are not linear. You can represent them with words, with tables, with equations, with lists of ordered pairs, and with graphs. And to those of you who are struggling, this is very much a trial and error lesson. You just kind of try a rule. That's literally what we just did. You try a rule, it doesn't work, and you try again until you find one that does. We've been talking about patterns. Look for patterns in the different graphs you see. If you see that y is increasing way faster than x, then it's probably squared or cubed or even exponential, like this guy. However, if y is not increasing very fast, if it's linear, then it's probably linear. Anyway, I'm here to help. Let me know what questions you have. Take it step by step and have a fantastic time on your